Swayam Prabha. Digital India. Educated India.
And on the audio mixer. Sometimes you also have a simple strip of carbon, okay, and then there is a brush tap which we can move up and down. So they are slider pots. Okay, so you physically move the slider up and down to increase or decrease the resistance. Okay, so that would be we would do something like that to change master volume control. Okay, to touch the master volume control, we would increase or decrease RF value. Now somebody complained that, hey, the male vocalist, I'm not able to hear very well. So then let's say the male vocalist is connected to V2, then you can change this resistance. So all these resistances are actually, we can program them, we can move them up and down. So sophisticated instruments have them electronically programmable, and a manual instrument would have a physical resistance which you can change up and down. So in this way, we can actually change the gain of the each and every input. So very commonly used circuit is called audio mixer. Now I want to take a diversion here of the term mixer. Okay, now when we think of mixer, we think about mixer grinder, or you take few things together and you just mix them up, right? So this is what this circuit is doing. It's taking electrical inputs from variety of sources and just adding them together, mixing them together, and then you take the final output. In RF circuits, the word mixer means something different. In RF circuits, mixer means a multiplier. So I'm just telling you this story because then you would appreciate the word mixer and you won't get confused in case you hear it in any other context. So there in the RF circuits, what happens is, if you remember the radio example I gave you, the signal which is coming from the antenna is coming for, let's say, 460.02 megahertz. Okay. Now I can mix it, and in this case mixer means multiplier. I can mix with another signal which is a sinusoidal signal. It doesn't look pretty, but let me rewrite again. Something like this, and here I would mix it with, let's say, 460 megahertz. And when you mix two sine waves, right, so you get addition term and subtraction term. So our goal is to mix these two frequencies and then look at the low frequency term. So the low frequency term here will be, let's say, 20 kilohertz, and that 20 kilohertz is what we call as a baseband signal, and we process it. So in the context of RF circuits, mixer means multiplier, where we do frequency translation. And in the original example, when I was talking about mixer, it just means you add everything together. Okay, you mix everything together. Just a subtle thing you should know. Now we will move on to the next property or a definition, which is input and output resistance. So for that, let's say there is this box, and this is the ground. There is input and output. So when we want to measure input resistance, what we do is generally we apply a voltage source, a test voltage source at the input, and then we measure how much current is going in here, IT. And then we say that Rin is equal to V test divided by I test. All right. When we want to measure output resistance, we would take the circuit. Let's say this is input, output, and in this case we want to ground the input, analog ground the input, and then we would like to measure. This is our V test, and we measure what's the I test going in. So our output will be V test divided by I test. And this definition we will try it out on different circuits, and then we will understand the significance of input and output resistance. So let's take example of the amplifier that we just learned, which is inverting amplifier, and figure out input and output resistance. So in this particular case, minus plus. I would like you to pause the video right after I draw the circuit and then tell me, in your opinion, what is the input and output resistance. So if you apply V test over here, there will be current I test which will flow through this, and the same I test will flow through this, correct? There is no current going inside here. Now this node is virtual ground. So I test value is going to be equal to V test minus 0 divided by R1. So by definition, RAN is equal to V test divided by I test, which is equal to R1. Kind of makes sense, right? Resistance R1. And if you look at the output resistance, what do you think the value will be? So the key thing to note here is, if you look inside this amplifier, okay, inside the amplifier the model shows AV, VP minus VN. So this is a voltage source. Now the voltage source doesn't matter where it's connected. Okay, for example, it's connected to these resistors and all those things, right? If you look at the R in here, since for our analysis this is an ideal voltage source, in resistance looking inside an ideal voltage source is 0, Rn equal to 0. So we can say that, I should not use the word Rn here, let's drop that. I should use the word, since we already use the Rn here, let's call it, if you look at R out is equal to 0, because we have ideal voltage source at this point. So these are simple examples of input resistance and output resistance. Now we will do a different circuit. This circuit is called non-inverting. Non-inverting amplifier almost looks similar to what we have done before. Again, negative, positive. So there is a negative feedback here, R2, R1, except that the input is applied in a different location. So this earlier case, we connected to analog ground and we apply voltage at this point, plus minus, and this is my V in to the positive input. Okay, and this is our ground, and here is what we are measuring, our V out. So we can analyze this circuit saying that because of negative feedback, the positive and negative terminal of the op-amp is a virtual short. Here we will not use the term virtual ground because I actually have a voltage source connected to positive input. So there is a virtual short between these two. So Vp is equal to Vn, correct? Now our original equation V out was equal to AV Vp minus Vn. If Vp and Vn is a okay, if Vp so we can substitute here. We can say this is equal to AV and this is Vn minus Vn. All right. using this. So Vn is equal to V out divided by AV, and there will be a negative term plus V input. As we said again, if AV is infinite, then we can say that Vn is equal to Vn, and that's the virtual short we were talking about. Now let's look at the KCL at Vn node, this particular node. The KCL says that, let's say the current I1 is flowing this way and the current I2 is flowing this way. So I1 is equal to I2. This will give us V in divided by R1 is equal to V out minus V in divided by R2. Remember, we have to look at the voltage drop across the resistor. Voltage drop across the resistor is V out on one side and V in on other side. That's why we have V out minus V in divided by R2. Now if we again do this analysis, you will see that V out divided by V in is equal to 1 plus R2 divided by R1. So in this example, again, we have assumed that AV is extremely large. Again, if you look here, there is no negative sign, so it's a positive sign, and hence it's called non-inverting amplifier. If you remember, in the previous example, we did effect of finite open loop gain. I would like you to go through that. I will take a pause here. Just substitute, follow the same train of thought. Instead of assuming AV is infinite, just keep AV value as is and substitute in these two equations that we just went through on a piece of paper and come back with value of gain. You can pause the video and so what you will be doing would be effect of finite open loop gain AV and the closed loop gain G, the value of which you will tell me. So what you will see is the expression for the gain looks very similar, R2 divided by R1. So this would be your non-inverting gain, and in the denominator a similar term appears, which is 1 plus R2 divided by R1 and reciprocal of AV here. So same way, if we want to keep this gain, closed loop gain, independent of the AV, then AV has to be much greater than 1 plus R2 divided by R1. And in that case, we can approximate this equal to 0, and then we get 1 plus R2 divided by R1 as our gain term. You can also convince yourself. So interesting thing about this amplifier is, what is Rin for this amplifier? First of all, what is In for an ideal operational amplifier? For an ideal operational amplifier, we have went through this before. In is equal to 0. There is no current going inside. It looks like a totally open circuit. So as a result of which, Rn for this amplifier is going to look like it's infinite, and Rout, as I said in here, is going to look like 0, purely because there is a voltage source inside which is driving the output in that model, right? So the good thing about this non-inverting amplifier is Rn is equal to infinite and Rout is equal to 0. So as you can see, this is very much desired, and this is what we always like, is input resistance should be infinite and output resistance should be 0, so that we can there is no effect of loading due to this particular operation amplifier circuit. So keep that in mind. Now we are going to talk about some new terminology. I'm going to introduce this terminology to you right now, so that things get easier for you when we move along. If you remember the example of ECG, okay, so we had an amplifier, okay, and what we are trying to do is a difference amplifier. Again, so if there are two terminals, in this case we just call them plus and minus, and we are applying, let's say, V1 and V2. Then we would like to amplify the difference between the two. However, anything to do with any common signal between these two terminals, we don't want to amplify. Now take one step back. If you remember the previous example, we said that if you apply V1 and V2 as two inputs, then we can look at difference signal as VID is equal to V1 minus V2, correct? And what is a common signal? VICM, that would be V1 plus V2 divided by 2. Got it? So I can solve these two equations and come up with V1. I can write it as VICM plus VID divided by 2, and V2 I can write it as VICM minus VID divided by 2. So that's a trick we use all the time as circuit designers, is if you have two different voltages V1 and V2, then we kind of split them in common mode signal. This would be our common signal and this would be our differential signal. And we know that this output voltage, Vout, will respond to both. It will respond to the common mode and differential mode. So in reality, Vout will be equal to AD times VID plus ACM times VICM. So the output voltage is function of differential voltage as well as common mode voltage. And the gain for differential voltage is given by AD, and gain for common mode voltage is given by ACM. So this is our differential gain and this is common mode gain. Now for ideal amplifier, if you remember the example of ECG, we wanted this to be, AD to be very large, okay, and we want ACM to be 0. We don't want anything common mode that 50 hertz hum in your body, which is being applied to both plus and minus terminal. We don't want that to come outside. Okay, so we want ACM to be ideally you want it to be 0 and this as large as possible, AD. Okay. So the new term I'm going to introduce early on for you is how good that amplifier is for this particular property, and it's called common mode rejection ratio. And common mode rejection ratio is how good this amplifier at rejecting the common mode signals. So definitely it is something is given by ratio of AD versus ACM, common mode. So we want ACM to be 0 and AD to be large, so this number should go to infinity. Now these numbers can be very high, so let me take one different step to introduce one definition for you, and the definition is decibels. Okay, so dB is applied to ratios only. Remember that you cannot take dB of 1 volt. You always take dB of ratio of two voltages. All right. So the dB term is defined as 20 log to the base 10 of a ratio. So 0 dB means, what does 0 dB means? This means this ratio is equal to 1. Okay. And if this ratio is equal to 10, then this would be the log 10 log of 10 to the base 10 would be equal to 1. So this would be 20 dB. So the ratio here would be 1, ratio of 10, ratio of 100 would give you 40 dB. Ratio of 1000 would give you 60 dB. Ratio of 1 million would give you 120 dB. All right. So you can see we can deal with really large variation in numbers in terms of ratios, and capture them with this compressed scale called dB. All right. Now the common mode, the reason I'm saying this is the common mode rejection ratio, you generally CMRR, you generally mention it in dBs, and it's 20 log AD divided by ACM, and as I said again, it's ideally. Next thing we go and talk about is a combination of these two ideas, and that would be a stopping point for this particular lecture. So we learned a inverting amplifier, we learned a non-inverting amplifier, and now we're going to come up with a circuit which kind of combines the two ideas. So let's see how that looks like. So if you remember, when we were doing a inverting amplifier, the circuit looked like this. So this is where my V input 1, this is R1, R2, minus and plus. And now I'm going to add another circuit here, simple circuit. So this is R3, R4, and I'm going to apply VI2 here. And this is my V out with respect to ground again, analog ground. So how do we analyze this circuit? This looks, suddenly I have made put 4 resistors and circuit looks a little bit complicated. So whenever things get complicated, we simplify. And one way to simplify is using superposition theorem. So you can say that if first let's just apply Vi1 and keep Vi2 equal to 0, then you can quickly see that Vo is equal to minus R2 divided by R1 times Vi1. Straightforward. Now I'm going to put Vi1 is equal to 0 and I'm going to apply Vi2 over here. Then you would quickly tell that this node is going to be, looks like a resistive divider. So the Vp node will be equal to R4 divided by R3 plus R4 of Vi2. And from here onwards, it looks like a non-inverting amplifier. Since Vi1 is equal to 0, so we will multiply this by 1 plus R2 divided by R1. Okay, so now we have two terms. So this would be your VO due to Vi2, and this would be, let me use a different color. So this would be your VO due to Vi1, and this would be your VO due to Vi2. So let me repeat again if it's not clear. When Vi2 is equal to 0, for superposition we turn on one source at a time and we derive the transfer function to the output, and then we add the two together since the circuit is linear, right? So when you are applying Vi2, this particular potential at the positive input is going to look like this. It's a voltage divider equation, R4 divided by R3 plus R4 times Vi2. And we already learned the gain for non-inverting amplifier when you apply certain voltage at the positive input, and that was 1 plus R2 over R1. Okay, so that's the way we got this particular expression. So now in reality we would like to keep both the gains same, because we would like to subtract the two inputs and amplify them together, right? So the gains for both of them, both the paths should be equal. Otherwise you will not get that subtraction effect. You will get one will be scaled version and other one will not be scaled version, something like that. So there will be a difference between the gain in either Vi1 or Vi2. To keep the gain same gain, we can write another equation. Keep same gain for Vi1 and Vi2. Mind you, one of them, this is an inverting input and this is a non-inverting input. So the mod of the gain should be same. In that case, what you will get is R4 divided by R3 plus R4 times 1 plus R2 divided by R1 is equal to R2 divided by R1. That's our desire. And if you solve this equation, you will quickly come to conclusion that R2 divided by R1 is equal to R4 divided by R3. So if I make these resistors equal, which is R1 is equal to R3 and R2 equal to R4. So what we have to do is R1 is equal to R3 and R4 is equal to R2. If we follow this, then we get this same ratio for both paths, and you can quickly prove yourself that output voltage Vout is equal to R2 divided by R1 and then Vi2 minus Vi1, which is R2 divided by R1 times Vid, difference potential. The reason I'm showing you this circuit is your output now is completely independent of the common mode voltage, because it only responds to the difference between the two. So since VO is independent of VCM, you get ACM will be equal to 0, and our desired property is CMRR should be infinity. Okay, we'll stop right here. Thank you.